Good morning and aloha.
Aloha.
My name is, like Dr. Bruder said, my name is Krout. I'm a senior here at BYU Hawaii, majoring in pre-professional biology with a minor in biochemistry. Dr. Randy Day has been my mentor, and I'd like to thank him in advance for helping me with my research. The title of my research is Using Chia to Enhance Prolonged Aerobic Activity. During my time here at BYU Hawaii, I've had the opportunity to be on the men's cross-country team. Because of my running habit, I've looked for different ways to improve and enhance my running performance, legally, of course. And because of that, my search led me to something called chia, which was supposed to be the next miracle food that all endurance athletes needed to incorporate into their diet in order to improve their performance. And so I decided to put chia to the test to see if all those claims were true and to see if there was any scientific proof behind it. And so this is my research. Chia, or Salvia hispanica, is a flowering plant in the mint family, native to Central America. It was cultivated by the Aztec and Mayan cultures. And Aztec folklore suggests that an Aztec worker in the mornings before leaving his hut to go to work would take a sample or a serving of chia seeds mixed with water and lime juice. And that would give him enough energy to go throughout his daily chores and tasks without needing a break to get more food before he came home again. The reason for this is that the chia seed contains a very large amount of fatty acids. It actually contains 13% of the daily value of alpha-linoleic acid. And as we know, when fatty acids are oxidized, they yield very high amounts of ATP and calories, which gives you a lot of energy. Also, fatty acids are stored very easily in the body because they don't need any water to be stored, and you basically have an unlimited storage capacity for fats. Previous research that had been done that I had based my research off of, there were two experiments. One was on long-distance migratory birds, done by Dr. John Michael Weber in 2008. Dr. Weber studied the sandpiper bird, more specifically its migration from Canada down to South America every year. What he noticed was that a few months prior to the bird's migration, it started to do is what he called natural doping, where it would change its diet to sources that were very rich in fatty acids, such as different insects and different seeds. He also noted that just before they took off on their migration, the fatty acid stores of these birds had doubled in size. And this, he concluded, is what gave the birds enough fuel and energy to propel themselves down from Canada to South America every year. The second study I followed was done on endurance cyclists, done by Dr. E.V. Lambert et al. In 2010. Dr. Lambert and his team took a group of endurance cyclists and had them go on a high-fat diet for 10 days. Following their 10-day splurge of fat, they had a day of carbohydrate loading. The following day, they had them do a 20-kilometer time trial. What Dr. Lambert and his team found was that at the end of the time trial, the cyclists had improved an average of 80 seconds. And they also reported a twofold resistance to skeletal muscle fatigue. What Dr. Lambert and his team were therefore able to conclude was that using fatty acids as a fuel source prolonged the onset of skeletal muscle fatigue. So I took these two researches and I developed my own hypothesis for runners. What I hypothesized was that a high-fat fuel source like chia seeds would yield higher rates of fat oxidation. Higher rates of fat oxidation would therefore yield increased muscle glycogen stores, and increased muscle glycogen stores would therefore yield faster times over a 10-kilometer distance. So I enlisted the help of the BYU Hawaii men's cross-country team, and I got 7 runners to participate. They were all between the ages of 21 and 27, and all had the same general background of training. I gave 4 of the runners a 236 milliliter, about 10 ounce sample of chia mixed with water. I gave the other 3 runners a 236 milliliter or 10 ounce sample of tapioca pearls mixed with water as well. I had all 7 runners drink their respective cocktails, and then I took them over to the fitness center and put them on a treadmill. I had them run a glycogen depletion workout at 65 to 75% of the VO2 max. Following their workout, I took them to the BYU Hawaii road course, where I had them run a 5-kilometer time trial. I took the results of each of the times that they finished in, and I gave them a 10-minute resting period where they were able to catch their breath, drink some water, do some stretches maybe, but that was it. I then put them through a gauntlet and had them run a second 5-kilometer time trial, where on the same course, and I reported their results. I then had them observe a 2-week washout period. Basically, they were supposed to continue with their normal everyday lives. Normal running habits, normal eating habits, normal sleeping habits. I had them come back to the fitness center, and I ran a crossover protocol. Basically, that means that the runners that took the chia cocktail the first time switched and took the tapioca this time. And the ones that took the tapioca the first time took the chia the second time. I had them do the same exact glycogen depletion workout on the treadmill, following which I had them run the first 5-kilometer time trial, gave them a 10-minute break, and had them run the second 5-kilometer time trial. So at this point, you can imagine they're pretty sick of me, but I have all their times, and so that's all I need them for. I then used a paired t-test to take their times and analyze them. Now for the analysis with the paired t-test, what I did is I took the first 5-kilometer time trial when they had chia, and I compared it to the first 5-kilometer time trial when they didn't take chia. And then I compared the second 5-kilometer time trial when they had chia compared to the second 5-kilometer time trial when they did not have chia. So as you can see up here, Table 1 represents the times and minutes of the runner's first 5-kilometer time trial. Each of the runners are represented here with their respective 5-kilometer time trial runs. The asterisk signifies that they took chia before that workout. Figure 1 is a graph representing the data here on Table 1, or the times for the runner's first 5-kilometer time trials. As you can see, each runner is represented here with their 2 first 5-kilometer time trials. The blue color is the chia, and the orange is when they did not take chia. From these numbers, a p-value was generated of 0.368 with a standard deviation of 3.32. The average time for the runners when they took chia was 19.35 minutes, and when they did not take chia was 20.37 minutes. Then I analyzed their second 5-kilometer time trials. As you can see, Table 2 represents their times for the second 5-kilometer time trials, with each runner represented here and their corresponding 5-kilometer times. Once again, the asterisk symbolizes that they took chia on that 5-kilometer run. Figure 2 is the graph of this data with each individual runner represented with his 2 second 5-kilometer time trials. Once again, blue signifies that they took chia, and orange signifies that they did not take chia on that time trial. For this set of numbers and times, a p-value was generated of 0.368 with a standard deviation of 4.15. The average time for the runners on chia was 20.01 minutes, and without chia was 19.47 minutes. Because based on my protocol, and therefore the data that was generated, I could therefore conclude that taking chia as a supplement before a 10-kilometer time trial does not significantly aid or benefit a runner. The reason I chose this protocol was because it was significant and relevant to me as a collegiate runner and also to the BYU Hawaii cross-country team. 10 kilometers is a distance that they run for their races. So it's something that I thought would be very useful to them in preparing for their competitions. I would propose that a more arduous protocol could be used to truly induce skeletal muscle fatigue and would therefore yield some other interesting results. For example, I think that a possible 2 studies could be done because of my research. The first one would be to increase the distance run during the muscle glycogen depletion exercise. I think it would be interesting to have the runners run 20 miles and then have them afterwards run a 10-kilometer time trial. This would yield a perfect 26.2 miles or a marathon, and so it would be very relevant to marathon runners and also ultra-marathon runners. Once again, it would be very important because you'd be able to know when skeletal muscle fatigue actually does happen and what is a good fuel source for an event like that. A second study that could possibly be done would be one that was like Dr. Lambert's with his cyclists. I think it'd be interesting to get a group of runners and have them go on a high-fat diet for 10 days, following which they could have a day of carbohydrate loading, and the following day they could run their marathon time trial. I think that would also give very interesting results as far as what fuel is necessary and when skeletal muscle fatigue really does occur. So I'd like to thank Dr. Randy Day once again, my mentor, for his guidance in helping me with this research and interpret the data. I'd like to thank the BYU Hawaii Biology Department and faculty for their input over these past couple semesters of my research. And I would also like to give a special thanks to Kevin Schlag and the BYU Hawaii Men's Cross Country team for their help and participation in this research.